Hello everyone, my name is Eva, and today I will talk about public randomness. This is a joint work with a team from EPFL, Yale University, and University of Bonn. So my talk will consist of 4 parts. I will first motivate why we actually decided to look into public randomness. I will tell you about 2 protocols we propose that target 2 very different deployment scenarios. I will tell you a little bit more about implementation, our results, and our current deployment. So let me tell you what public randomness is and why generating it is actually quite hard. So public randomness is very different from private randomness we're all used to. We typically use private randomness to generate our private keys, for example. Public randomness, on the other hand, is collectively used, right? We want that public randomness to be unpredictable ahead of time, but at some point when we're ready to use it, we'll reveal that and it won't have to stay secret past that point in time. And clearly, when it comes to public randomness, entropy is not enough. Just the quality of randomness in terms of entropy won't get us where we want to be. So what do we use public randomness for? Turns out there's a number of applications of public randomness. We use them for random selections. You can think of lotteries, auditing elections. You can use public randomness for decks and team assignments in games, crypto, challenges in zero-knowledge proofs, authentication, nothing up my sleeve numbers. And lastly, protocols, something that is probably most relevant to you guys. You can use public randomness for sharding, as it's done on Ledger, that you will hear about right after my talk, but also for leader election in consensus protocols for proof of stake. So unfortunately, while it seems that public randomness is an easy concept, we've had a number of examples of failed or rigged public randomness. For example, in the Vietnam War lottery, dates representing birthdays were not sufficiently mixed, so if you were born in December, you were more likely to be drafted. Hot and cold balls were used to rig European soccer competitions. They would pick a team based on how the ball felt to touch, not something that anyone could be able to see. And lastly, an insider hacked a pseudo-random number generator to predict numbers or pick numbers in the Megabucks lottery. Then he tried to anonymously purchase a ticket with those specific numbers and collect a reward. The problem here is that because of a good lack of mechanism for public randomness, we can't implement fair and good public choices. And it turns out that public randomness is not a new concept. There has always been a need for it, and perhaps many years ago a big book of numbers published by a reputable source was enough. Today it's not. Today we face 2 issues of trust and scale, and in this work we addressed both of these issues. So we set out to achieve a decentralized public randomness in the very well understood and familiar to most of us threshold security model. We had 5 specific goals in mind. First, we wanted availability. We wanted to ensure that we can successfully complete the protocol even in the presence of faulty nodes. Unpredictability is needed to ensure that output is not revealed prematurely. We wanted to be able to tell exactly when parties will receive randomness. Unbiasability, we want the output to be distributed uniformly at random. Verifiability is something extremely important to public randomness. We want everyone, not only those participating in the protocol, to be able to check the randomness. And lastly, scalability. We wanted to run the protocol with potentially hundreds of participants. So there are 2 main approaches to public randomness, those that require trusted third parties, such as NIST randomness beacons, and those without it. The ones without it include Bitcoin, slow crypto hash functions, lotteries, and other data. While those do work, they often rely on new, unusual, or not fully believed assumptions. The 2 approaches that share our threshold security model include coin flipping and DKG, distributed key generation. They do work, however, they don't scale well past maybe tens of participants. So on the surface, it seems that generating public randomness is easy, right? You can simply take random inputs from all participants, and there's this false assumption that so long there is one honest participant, that will sufficiently randomize the output. Unfortunately, it completely doesn't work because the last node has full control of the output. They will simply wait to see what other inputs are and will pick their own input as a function of it. So we achieve no security. We can address this issue with a commit and reveal scheme, right? Where we have everyone choose their input up front before seeing anything. Unfortunately, a dishonest node can refuse to reveal their share upon seeing what the output of the protocol is going to be. If they don't like it, they can force a rerun, and that constitutes a bias. And this availability issue can be addressed using secret sharing, such that we can recover those inputs even if the adversary is not cooperating with us. The problem here is that the adversary can set bad shares, let's say to some honest nodes, and that means that not every node, honest node, will recover exactly the same random value. So this brings us to RunCharm, asynchronous leaderless protocol that basically uses verifiable secret sharing to force all of the nodes to distribute consistent shares. While we do get availability, unpredictability, and unbiasability, we still don't have public verifiability and scalability. And we wanted to improve on these two goals. So that's exactly what was the goal for the two protocols I will tell you about, Ronhound and RunHerd. They both achieve all of the 5 properties in slightly different ways because they're meant for different deployment scenarios. So the goal of Ronhound was to provide public verifiability by third parties and, of course, improve on the performance of RunCharm. Ronhound is designed to be a client-server protocol where the client is using a potentially large set of servers to scavenge randomness from. The beauty here is that the servers are nearly stateless. They're simply used by the client, and the client can be used different servers from run to run. We have a config file that is announced in advance, and with respect to that config file, we're gonna is it okay? We're going to run our protocol. So imagine a scenario where you have a lottery authority and they want to pick a winner in a fair and verifiable way. Such a run is typically announced publicly in advance. Then the lottery authority would be a client in our protocol, and they would use a set of independent parties to aid them in generating this randomness. The output of the protocol would be the chunk of randomness that we need to pick a winner, as well as a protocol transcript that will testify to or attest to the correctness of that randomness. So how do we achieve public verifiability? We do it in two ways. First, we use PVSS, publicly verifiable secret sharing, that improves upon regular VSS by adding encryption and zero-knowledge proofs. This means that anyone can look at the shares and anyone can check the shares without actually getting access to them. We also use collective signing to hold the client accountable and allow client to make a decision and publicly commit to that decision. Collective co-signing can be implemented using an aggregate threshold or multi-signature. In our implementation, we use Schnorr multi-signatures. So what's going to come out of the protocol again is the randomness and the transcript of the entire protocol run, because of this interesting property we have here that the client communicates with the servers directly and none of the servers talk to one another. This means that the client gets the entire view of the protocol, every single message that is sent and received and is needed to replay the protocol for verification. So scalability, right? I said we use PVSS. However, sharing with everyone is expensive. In my scalability goal, I told you that we want to run this protocol with potentially hundreds of participants. Sharing with everyone is simply too expensive. So the idea here is to shard the participating server into PVSS groups, then have every single group produce a secret, and have our randomness to be a function of all groups' secrets, right? The question here is how to securely assign participants to the groups, right? I told you that this is a randomness protocol, and most of you would tell me that the best way to do the sharding is randomly, right? So how do we address that problem? Well, it turns out that it actually doesn't matter if the client picks the groups in an arbitrary way. If we look at a client putting together those groups in terms of availability, right, the client can self-DOS itself if he puts human and malicious nodes into each group. However, for security, making sure that the outcome is unbiased, this is completely irrelevant. Due to the pigeonhole principle, we know that regardless of how the client assigns nodes to the groups, there will be at least one group with higher than average number of honest nodes, right? And that will be the group that holds a secret that the adversary cannot prematurely get access to and bias in any way. We also use collective signing, as I mentioned, to commit client to his choices, so he cannot play backsies and go back and say, I don't like this randomness, let me try something else. So let's briefly step through the protocol so you get a better idea how it works. First, the client puts together a config file that includes the names and the public keys of all the participating nodes, and also that's where the client assigns every node to a group. Then each node finds its group members. They pick their own secret, and they secret share using PVSS to only their group members. The nodes then take those PVS shares and send them back to the client. They also start the phase 1 of the collective co-signing. I mentioned that we're using multi-signatures, so we have to do commit, challenge, and response. They're basically starting the process early on to certify the client choice later on. So the client will sit there and wait for those PVSS shares to come. He will verify them, discarding any shares that are not correct, right? And once he has sufficiently many shares from every group, he will decide which inputs from every group should contribute to that group's secret. Notice that we're doing that without knowing what the secrets are, right? We only have PVSS shares. So the client will respond with the selection to the nodes and also with a commitment for the collective co-signing. All the servers will verify that the client's choice is valid, that the client picked at least F+1 inputs from every group, and they will produce their cozy response. They will produce their partial acknowledgement that they checked the choice and it's okay. The client will then wait for those responses to come. Those responses will be aggregated into a multi-signature. And once the client has 2F+1 of those acknowledgements from participating servers, he will take that multi-signature, send it to all the servers, and ask for decryption of their secrets. Each node will verify that, again, at least 2F+1 other nodes approved of the client choice, and they will start the process of sending the client the decrypted input values. The client then will simply gather the input values from every group. It will reconstruct each group's secret, and then, in turn, the collective randomness, which is simply a function of every single group input. As an output, we're going to produce that randomness as well as the kind of log of the entire protocol, which consists of every single message that can be checked by anyone. Remember that the servers are stateless. The only state they hold are their private keys. So what do we achieve through this protocol? Well, we get all 4 properties, including public verifiability, and the complexity is acceptable. It's linear in the number of nodes, assuming that we are sharding into constant groups of size C. So far, I told you a protocol that is giving you randomness on demand, and the protocol is run by a client who is fully in charge and fully responsible for it, right? That doesn't kind of fit every deployment scenario. So our second goal was to kind of create this randomness beacon, a protocol that will give us a series of random values kind of in more continuous way. Specifically, we also wanted to improve on the public verifiability, both in the time it takes to do so and in the size of the proof. Ideally, we wanted it to be a single Schnorr signature to have a constant verification time. And of course, we wanted better performance because that's what we always want. So we built RunHerd as a randomness beacon. RunHerd is built upon a collective authority, which is basically a bunch of servers working together in an efficient and publicly verifiable way. RunHerd relies on a leader. However, leader is only trusted with availability. We're not assuming it's honest, we're simply assuming it's present, right? The leader simply coordinates the run among all the other nodes. So the main idea behind RunHerd was to create our collective randomness at this continuous stream of collective Schnorr signatures on some value. The benefit of that was definitely a small proof size. If you have a single signature, the size of it is small and the verification is quite small. And we wanted to get a better performance. So the problem here was that while it works, we achieved the goal of better performance because we're communicating on a tree, so it's log n, and the fact that the signatures are easy to verify, we weren't completely bias resistant. If we simply take every single node and we expect every node to always produce the value, then things really don't go well if one of the nodes is offline intentionally or otherwise. Because of one missing input, the resulting signature would be different, and that would give the adversary the ability to selectively affect the randomness that comes out of the protocol. So we had to address this availability issue, which we did by using threshold Schnorr signing. Threshold Schnorr signing allows you to create this multi-signature with only T out of N no presence, right? So we were able to tolerate some failures. We have kind of arranged nodes in groups, right? Every group is producing a signature so long T nodes are present, so we are able to tolerate a fraction of nodes being unavailable in each run. And RunHerd has two main components. Setup, that is run once, is pretty expensive, but afterwards we're able to produce randomness in a pretty efficient way. So setup, we simply want securely assign nodes to groups and kind of bootstrap the entire process. Setup is followed by many rounds of randomness, and it consists of four steps. So first, we pick a temporary leader. We can do so by simply picking someone with the lowest ticket generated using a VRF. That node would simply be a leader used for the initial step, just the bootstrapping of the process, not the leader who is later on responsible for randomness generation. That leader would actually use our previous protocol, Ronhound, to get a chunk of good randomness that we're going to use as a sharding seed. So this temporary leader plays the role of a Ronhound client, and the other servers participate in the usual server role. And that seed again is used to shard participants into groups. And notice that this assignment is not biased because it's done using unbiased randomness that came from the other protocol. Once we have those groups kind of assigned, we need each group to produce their collective group key. So every group has this collective key that they will be using to produce some output out of that group. Then we take all of those keys, we combine them together, and this becomes this collective RunHerd key under which we'll be issuing those continuous collective signatures that will serve as our randomness. That collective key is certified by all servers in a run of collective co-signing, which means that we can discard the protocol that the transcript that comes out of Ronhound and simply have this key endorsed and believed by third parties. So how does the randomness generation work? Once we do the heavy lifting in the setup phase, randomness generation is actually pretty easy. We simply have the authority leader, again, kind of picked using this unbiased randomness, broadcast a series of timestamps, and each group will simply produce their individual signature on that timestamp. The signatures will be collected and then combined together, and that will be our randomness. So notice that what we're achieving here is this ability to simply push some value down the communication tree. Every group produces their small signature. We take the signatures together, and comes our randomness. And that gives us really good verification, right? Because RunHerd produces a single Schnorr signature, then anyone can efficiently verify the pair that comes out of the protocol under the collective RunHerd key. It's constant time and really small size for the signature. So in this case, RunHerd allows us to achieve all the properties we set out to achieve, including reasonable performance. Performance is logarithmic in the number of participants, again, under the assumption that we have a constant group size, C. So let me tell you about our implementation and where we are when it comes to deployment of our randomness beacon. So we implemented both protocols in Go using the DD's lab crypto libraries. We run experiments on the Terra lab using 32 physical machines, and we of course restricted network conditions to simulate more real-world conditions. So we looked at the randomness generation and verification time in Ronhound. We run our experiments up to 1,024 nodes in groups of varying sizes. So the takeaway in Ronhound with 1,024 nodes in a group size of 32, generation takes around 290 seconds and verification takes 160 seconds. We also looked at the CPU cost for both the client and the servers in exactly the same setup. And the total cost for one Ronhound run is around 10 CPU minutes, which translates to change on EC2. And again, that was done with 1,024 nodes with groups of 32 nodes. For RunHerd, we only looked at randomness generation time because verification is constant, so there was really no need to look into that. And as a takeaway, generation for RunHerd takes around 6 seconds, but that after one time setup of 10 minutes. And those 10 minutes, again, are coming from the fact that we have to run Ronhound first to get this good chunk of randomness to bootstrap RunHerd. I would like to tell you now about the actual deployment of our randomness protocol. It turns out that a lot of people are quite interested in public randomness. It turns out it's a pretty useful primitives to have. So we wanted to have a distributed version of this kind of randomness as a service. We called it Durant, not very creatively, but gets the job done. And it's available on GitHub. So what Durant is actually a protocol that implements the logic of RunHerd in a slightly different way. Again, RunHerd kind of implement as Durant has a setup phase and then randomness generation. In setup, we're actually using threshold distributed key generation such that we can create this collective key under which we'll be issuing signatures that again will become our randomness. It's a threshold scheme which allows us to produce those signatures only when just a fraction of the nodes is present, right? And what comes out of this distributed key generation protocol is one collective key known to everyone, and kind of secret shares of the private key that are held by individual nodes. But the entire secret private key is not known to any single person. The beauty is that we can also refresh those shares of a private key, which kind of allows us to deal with churn, right? It's kind of unreasonable to assume that the set of nodes running Durant will never change. So this way, they can join the network, they can leave the network, and without changing the overall public key. So randomness generation is done using threshold BLS signatures, which gives us very good performance because it's a single round process. So we start by signing a fixed seed that it's agreed upon at the beginning of the protocol, and then we continuously sign the output of the previous round. The beauty here is that we follow this kind of three-step process of requesting a partial signature, waiting for T responses, reconstructing it, and then be able to immediately go to the next phase. And that also means that we don't even have a leader that is trusted with availability. Every node simply can wait for the T-shares on the network. The second they have them, they reconstruct randomness, and they issue a partial signature for that value. This also means that we can work in asynchronous setting. So where we are with the deployment, we actually have implementation in Go. It's open sourced. Our aim is to kind of have a very simple system to use, both to kind of participate and also for the users. Ideally, we would like it to be a one-step command where you can just fetch randomness the same way you can fetch current times for NTP servers. Deployment, we're currently working with NIST, Cloudflare, EPFL, of course, Kudelski Security, and hopefully others to run those distributed nodes all over. Kind of, we would like to have a node in every jurisdiction to kind of make not only the protocol trustworthy from the design point, but kind of have them all over the place. If you are interested in running a Durant node, do talk to us. We make it super, super simple for you to do that. So let me conclude and say that public randomness is extremely important. Unfortunately, we face issues of trust and scale. We propose two protocols in the threshold security model that achieve the 5 properties we identified as necessary for modern uses of public randomness. We have an open source implementation that I encourage you to have a look at. And with that, I'm very happy to take questions.
Thank you, Eva. That was really interesting. I'm always astounded as to how much thinking goes into generating unpredictable randomness on demand, and I'm really glad to see that you're moving towards offering this as a service. So right. That headache can be solved for a lot of people.
Well, that's the plan.
Yeah, so really interesting. I have some questions at the back. Perhaps we can start with the gentleman over there.
Yeah. What actually happens when the malicious nodes exceed your threshold?
When they exceed the threshold, well, if they do, right, then they will recover all of this, at least all of the secrets from the groups, and then they can predict the randomness.
Can they control it?
So depends, right? Depending if we are looking at Ronhound or RunHerd, right? In RunHerd, you kind of commit to the choices beforehand. There's this kind of intermediate run of collective co-signing. So really depending on kind of at which part of the protocol. If from the very beginning they control the majority of every single group, then all bets are off, right? Then they collaborate together, they pick whatever inputs they want, and comes out the output. But again, for kind of in both the protocols, we only need one group not to be controlled by the adversary, not all of them. All of them is for availability or liveness. When it comes to a safety, single group. Mm-hmm.
Yeah. So I was wondering.
Oh, I'm sorry.
Yeah. How could you envision this working in a decentralized system? So like, let's suppose that we wanted to use this for proof of stake, for example. Mm-hmm. You need randomness proof of stake. That might be a chicken and egg situation because you need, if you want to randomly choose the, how do you choose the set of participants in your protocol in a random way? And if you choose it with proof of stake, that might cause a chicken and egg situation because proof of stake needs randomness. And also, like, do you think that maybe the authority of the leader groups could be replaced by a smart contract to get rid of that availability assumption? Because if you have that availability assumption, then if you elect leaders and they go offline, they could potentially bias the randomness by refusing to participate if the randomness is not in their favor.
Okay, so there's a bunch of questions, right? So to start with, right, how to pick those nodes that participate, right? Well, it's an open question, right? It's you could start with some. So the beauty here is that you can use as big of a set as you want, right? So you're not limited to just a handful of selected nodes. So if you really want, you can just let everyone participate, right? At least in the initial stages, if that's what they want, right? Your second question was about kind of the leaders and them being able to bias the output. They're not able to bias the output. Even if they don't, they refuse to participate, right? They're simply, they will stop the protocol early enough, right, that none of the random choices will be out. And if you look at Durant, right, Durant is run in a completely leaderless way. It's just this continuous, so long there are T active nodes, right, we can kind of make progress, and they don't have to be coordinated by a single leader.
Right. So what happens if the leader becomes unavailable? Do you have to elect new leader?
You do have your change.
Yeah. So my point is, like, if I'm elected as leader, I don't like the result. And let's suppose like 30% of potential leaders are malicious. They could potentially bias the result a bit.
But by then there's enough information propagated in the network that they can reconstruct that randomness themselves.
Right.
So it would just take a little bit more time, we'll do a view change, and then the next leader would reconstruct the randomness from the previous round. So would not do a rerun of the protocol, right? It would take us much longer to get the previous round's randomness. So yeah, so you kind of delay things, but don't bias things.
There's another question here.
Mm-hmm.
I may have just lost the point in there, but in Ronhound, you said that the servers were not talking between them, right? So basically, you have the client, he sends the information to the servers, the servers generate the thing, and they send it, right? But what actually prevents them to talk between themselves? So
no, they're welcome to. If that's what they want, right? They're welcome to.
But that's the point. If you can bias other groups by just like talking between themselves.
Well, they would have to be malicious, right? If they're malicious, they absolutely can talk to one another, right? Kind of under our model, we assume that the malicious servers are cooperating together, right? Honest servers won't, and if they simply don't want to send the messages direct to the client, they want to gossip it, that's perfectly fine too, because we're using PVSS, Evershare is encrypted, so even if it's you can put it on public blockchain for all we. Yeah.
Even if there's a malicious participant in every one of the groups, is that right?
Yeah, because also every group has a number of nodes selected from it to contribute to that group's randomness. Right. Even if you have a certain number of dishonest nodes in that group, they will only reveal their own inputs that contribute to the output of that group. They won't know the other inputs, right? So they will not be able to control the output of that group. That's exactly in Ronhound. We need one of those groups collectively to be honest, not each individual node. Okay. So long that happens, the whole thing cannot be biased.
Right, cool.
Yeah, thank you.
One more question. So, did you guys think at all about having nodes appear in shards appear in multiple shards to increase the probability of having one honest group?
Yeah, that's actually, it's problematic, right? But because you also, you increase the probability that dishonest nodes will appear many times, right? So it's much harder to reason about applying the pigeonhole principle that guarantees, in fact, that one group will exist. That's definitely something you can, we looked at, but it turns out that we can't have this, hard guarantee of one group for sure will be uncorrupted in our model.